Or you can unmute. Yeah. Okay. So first, I'm going to give a little introduction on Google Colab. So right here you can see I've opened the Google Colab, and Google Colabs, we have two things. We have a text cell and a code cell you can see up here. So you can see all of these are text cells where you can just write stuff. And there's a lot of, for example, these are all headings. That is too much to teach. So if you want to like have some fun formatting for the competition or for future uses of Google Colab, you can search how to do certain like titles and all of that. But for the text cells, there's also, for example, here you can there's some special characters for you to make the text, for example, code-like. Okay. But the most important thing for Google Colab is the code part. So you can see here I can create a code cell. So for Google Colab, it is Python code. So it is not like Java or C++. If you've learned that before, it is Python code. So and the good thing about Colab is it has memory. So let's say we just define a equals 3, and let's just run it. You can click the left button. And then let's just print out a. And you can see it's 3. But if I now do a equals 5, I just set a equals 5, and then I run this cell again, you can see it is 5. So it has like memory. So that's usually a good thing, but also sometimes when you're doing code, sometimes you like change a lot of code and you rerun the same cell without rerunning the whole notebook. And because you changed and then you only reran your like the cell that you're on, sometimes the memory is still there and a lot of stuff is messed up. So like an example is we have like a equals 3. Let me just run it again. And then let's just say like a equals a plus 1 and then print a. So if I run it once, it's 4, but I just run the same cell again and it's 5 and then 6, 7, 8. So be careful of like this feature in Google Colab. Okay. Other than that, I don't think there are also some other stuff like you can code with AI like right here. You can open Gemini and all of that. But I think that is the most important things about Colab is a short little introduction. Okay, now let's get into today's notes. Okay, so today we're going to learn an overview of all the common machine learning models. Because for the competition, we want you to know many machine learning models so that you can select the best ones for your own data set, for your own topic. And most of these are accessible from a library called sklearn, called scikit-learn. So you do not, like yesterday and the day before, we showed you gradient descent algorithm on linear regression. But sklearn has done all of that for you. It will do that in the background. So you do not need to actually do the gradient descent algorithm. You don't need to do anything like that. sklearn will just train the model for you. So all we need to do today is first learn about some models and second, learn the syntax in code of how to use sklearn so that you can just employ this model and just use it. And you can also use AI to code for you, but you should understand everything. And we'll like you can use AI to help you with the syntax, for example. But we'll go through everything today. Okay. And other important libraries are NumPy, Matplotlib, and Pandas. If I'm not really learned that, that's fine. You can ask AI for help for the competition. But if you have learned that, then it should be pretty easy. Those are just like libraries for like NumPy arrays or Panda data frames if you have learned it before. Okay, so first, yesterday we talked a lot about polynomial preprocessing, which is just adding polynomial features on top of the existing features that we have to introduce non-linearity. Because many problems like a parabola, you cannot solve it with linear regression, right? Like we talked about yesterday. Okay. However, do not use polynomial preprocessing when some features are categorical. Because categorical, like let's just say you're multiplying two features. Well, yesterday we talked about one-hot encoding. It's just 1 and 0 and 1 and 0. When you multiply, it's usually just 0 times 1 will just be 0. So everything will be zeroed out, and that does not make any sense. And also squaring a categorical feature, that also does not really make sense. So do not do polynomial preprocessing on categorical features. And also be careful about polynomial processing when there are many features, because like we said, for just factor, like we have a degree of 2, for example, x1 squared, x2 squared, x3 squared, but also x1, x2, x2, x3, x1, x3. All of those, the more features you have, the number of new features that you add will just increase a lot. So be careful about that. And to prevent higher order engineered features like I just talked about, use standard scalar afterwards. Okay, from dominating. Okay. So polynomial preprocessing, first of all, it is definitely not a model, right? It is just feature engineering, but it does learn what features X string has. So you need to you need to give X string to the polynomial features right here. You can see here in the code. You need to give X string to that instantiated polynomial features from sklearn. It then applies the same transformation to X-test. And we talked about yesterday why we do that to prevent data leakage. So polynomial preprocessing, of course, increases model complexity to make sure, and you need to make sure to use regularization if you want to prevent overfitting, like we talked about yesterday. So here, you can see here from sklearn dot preprocessing dot is just what is in the library, or what is in the model, or what is of the model. So from the preprocessing like unit or like storage of sklearn, want to import polynomial features. And in this line is we're just instantiating uh instantiating a class polynomial right here. So we give it degree equals 3, so that is just x1 cubed, x2 cubed, x1, x2, x3, x1 squared x3, for example. And include bias, make sure to set it to false because the default is true. And if it is true, just add an all one column to X string. And usually you do not need to do that. Like in linear regression, we talked about adding the all one column, but usually we do not need to do that. Because for like linear regression from sklearn, it will do that for you. So make sure to not let this add a all one column for you. And then all you need to do is polynomial.fit transform. Fit transform is a function under polynomial. So we fit on X string and we transform X string. Then we just simply transform X test using what we learned from X string. So fit is also the same thing as learn in a lot of sklearn syntax. All right, now let's talk about standard scalar. So for standard scalar, we talked about yesterday, it is the z-score normalization. Let me write that really quick. So standard scalar is the z-score normalization that we talked about yesterday. It is very important in both machine learning and deep learning. Across all samples, each feature's mean and standard deviation will be calculated, and then we normalize by subtracting the mean and dividing by the standard deviation. Scaling prevents features with large magnitudes from dominating the loss function in linear regression, logistic regression, a lot of other models as well. And especially for models that you need to calculate the distance, like in KNN and KMeans, we'll talk about that today. So you don't want like big features with large magnitudes just dominate the distance because that feature might not actually be very important, but you're letting the fact that it has a large magnitude, has a large range dominate. So that is unfair. Okay, so for for standard scalar, all you need to do is sklearn. It's the same library under sklearn called preprocessing. And then we instantiate a scalar, and then we do the same thing, fit transform on the X. What this will do is it'll just calculate, it'll store the mean standard deviation from X string, and then normalize X string. And then when we do dot transform X test, it will use the same X string mean and standard deviation to transform the X test to prevent data leakage. Okay. Now let's talk about PCA. It is principal component analysis. Talked a little bit about it yesterday, but we can talk a little bit about it more today. So PCA reduces the dimensionality of data. So let's say the X string is n by d. We'll transform it into n by d new, where d new is less than or equal to d. So let's say like our original data is like this. It has like 3 features. These are the columns. Then we might just want to decrease the number of features to 2. So you can see here. So dimensionality reduction is to turn 3 features into, let's say, 2 features. And keep in mind that this is not feature selection. Feature selection is just we're gonna like drop one of the features because it's kind of no use or does not contribute a lot. But PCA does not like that. PCA, like we talked about yesterday, is called feature extraction. So it is use all of these 3 to make the 2. So it's kind of like in synergy, we want to make these 2. Okay. So the mechanism by which PCA works is it will take the top, it will form these D new features by trying to maintain the most variance. And I will talk about that right now. So data must be scaled before dimensionality reduction. Keep that in mind. So, and we usually scale data using the standard scaler right here. And use PCA when you want to visualize your data in, let's say, like 2 dimensions. You might find the data to be clustered. Then you can know that, oh, the right cluster is label 1, the left cluster is label 0. My machine learning problem is done. Okay, so here is the syntax for encode for how to import PCA. So right here, we want to use the decomposition library under sklearn to import PCA. And then here we instantiate a PCA model. And here we're saying the n components is 4. So let's say maybe our original data set had 15 features. So now we're compressing it into 4 features. So that you can set yourself. Same thing, fit transform. So it'll learn the characteristics of X string and then transform X string into 4 features, and then use those same characteristics to transform X test to avoid data leakage. And finally, you can also print out the variance, like it'll have like something called explained variance ratio, and you can see like each principal component, how much variance, like what percentage of the variance is retained. But that, if you learn more about PCA, you'll understand more, but right now we don't really need to worry about it. Okay, let me draw a simple diagram of PCA like last time. So basically PCA is just, let's say we have 2 features and the points are like this. We want to find a hyperplane to project the features onto it so that we have the maximum variance. So here is the projection. Here's the projection. Here's the projection. So our new points are this one, and this one. So you can see that when we project it all onto this 1D line, we've successfully converted our 2D data into 1D data. But some problems are if we use, let's say, this hyperplane, then you can see this point goes to here, this point goes to here. They're essentially the same point. They're very close. But actually, they're not very close because in 2D space, they're like this. So you can see that, of course, we're losing information, but uh, sometimes we have to do it to avoid overfitting, or if there's like a billion features, we want to try to decrease it to have faster training. So that is PCA. So we're just trying to find the best hyperplane to project it onto so that we retain the maximum variance. And like variance, for example, like I just said, maybe these 2 points are very close, then the variance is not very high because they're very close. And we know that like for like a data set, variance is just how far from the mean are the points. So if the points are very spread out like this, then that is high variance. That's what we want. We want to retain as much information as possible. Because when we reduce a dimension, it'll definitely erase some information. Okay, now let's go to linear regression. So for linear regression, yesterday we talked about, I showed you the code for linear regression from scratch, but we do not need to do that. We can simply import from sklearn. So of course, linear regression is the simplest of ML models, and through gradient descent, it minimizes loss function and achieves a line of best fit. It is we're trying to minimize the sum of squared residuals, right? That's the MSE loss. And we use linear regression when the output is continuous. So the common evaluation metrics, of course, are mean squared error and something called R squared score. That when you go to AP statistics, you'll also learn more about that. We don't have to dive deep into that. So MSE measures the mean of the square differences, yeah, between the true value and the predicted value. So of course, the lower the better because it's mean squared error, so the lower the better. And R squared, it measures how much of the variation in the y-test can be explained by the model. So for R squared, the higher the better. And it ranges from 0 to 1, with 1 being perfect. Okay. Uh, so for MSE and R squared, just keep in mind that R squared is basically only designed for linear regression, but MSE is very important. MSE is used all over deep learning, all over machine learning. So yeah. Okay. Next, the risk of overfitting is very low, of course, because linear regression is a very simple model. But for high-dimensional data, we can always use regularization for preventing the model to learn the data as random noise. And below we'll show ridge regression and lasso regression like we talked about yesterday, how to import them from StandardScaler. Also, you can also remove highly correlated features like what we talked about yesterday. So for linear regression, it is the library name is called linear model in sklearn, and we just import the model right here, instantiate the model right here, and the default parameters are all good, so you don't need to like specify anything here. Then just simply fit it. Fit it just means find the optimal parameters. And then we do model.predict on the test set, and we'll get the y-pred right here. For evaluation, sklearn also has it for you. You do not need to do any formulas. So it's under the metrics library. So just import MSE, R squared score, etc. And then all you need to do is give it the y-test y-pred, and it'll calculate it for you, y-test y-pred. Finally, you can look at the weights and the biases of the model after you've trained it. So of course you have to run this after you have run this cell, right? After you have trained the model. After you train the model's coefficients, that's the weights, that's the thetas, you can print them out. And also the intercept is the bias, which is theta of 0. So that you can also print it out. All right, now let's talk about ridge regression. So ridge regression, like we talked about yesterday, is just linear regression, but L2 normalization. So we add this term right here. And remember that this is I from 1 to D, so we're not regularizing the bias. Remember to never regularize the bias. Okay. So we use this for high dimensional data as there will be many weights and it is easy to overfit. So this just tries to make the weights be closer to 0, and when you're closer to 0, it means that each feature does not matter much. It means that we're basically not even worrying about the features. So that's why it is regularization. It's like regularizing the model. Okay, so this very simple is the exact same syntax. So again, in linear model, import just ridge, instantiate the model right here, and here is uh the alpha parameter right here is basically this lambda parameter right here. So if you have 1, that means it's just regularization. But if your alpha is 0, then that means no regularization. Okay. And then same thing. Fit on the X train and Y train, predict on the X test, and that's it. And evaluation and interpretation are the same as linear regression up here. All right, let's go to lasso regression. So for lasso regression, we talked about yesterday, that is linear regression with L1 normalization, and the formula is like this. So L2 normalization is the squared theta. L1 normalization, it is absolute value. So remember that as opposed to ridge regression, Lasso is better at making some features completely and exactly 0. So that's very effective for like feature selection. That kind of models feature selection, right? We're just completely ignoring. But for L2 normalization, like last time in the notes, I said it's a little bit more circular. Uh, if we want to prove why it is completely 0, there is a simple geometric like way of thinking, but that is a little bit too complicated for our class. So just remember that ridge regression is a little bit more circular, it's not as like diagonal as lasso regression, and lasso regression makes features completely zero. So it's a little bit more harsh. Okay, and then the syntax is the exact same thing, but just we have lasso here, and when we instantiate, we use lasso, and then everything's the same. Okay. Now let's talk about logistic regression. Logistic regression, like we'd said in the first class, just linear regression, but we have a sigmoid function because logistic regression is for classification. And I know that logistic regression, the name literally has the word regression in there, but it is for classification. All right. So we use logistic regression when the output is categorical, of course. And so how it works, like we said last time, if the linear regression predicts 0 or more, then the sigmoid will make it 0.5 or more, and then we predict the positive class. If it is 0 or less, then it's 0.5 or less, and then it's the negative class. That's for binary classification. And then we also learned last time that logistic regression is a linear decision boundary. Like, for example, here is all one class, these triangles and these circles are all another class. Logistic regression will try to find the best line. And when we go to higher dimensions, there'll be a hyperplane to separate, but it is a linear model. All right. The common evaluation metrics are what we discussed last time, accuracy, precision, recall, F1 score. And like last time, we also showed the confusion matrix, so you can also print that out using StandardScaler. StandardScaler will do everything for you. Once again, the risk of overfitting is low. For high-dimensional data, use regularization for permitting the model to learn the data's random noise. Yeah. So here is the syntax. Again, it is linear model because, of course, the logistic regression, we showed the formula. It is linear regression, but just put a sigmoid on it. So it's a linear model. Import logistic regression, instantiate it. The parameters are all good. You don't need to specify anything here. Like the default parameters are all good. And then fit the model on the X train and the Y train, and then predict. That's it. Evaluation, you can, from the metrics, again, from the metrics library under sklearn, you can get accuracy score, confusion matrix, F1 score, all of these. And then you just use these right here. You give the Y test, Y pred, Y test, Y pred, Y test, Y pred, and then you will get all of these important metrics. You can print them out. And once again, logistic regression, you can get the weights and the biases, the coefficient and the intercept. All right. Now let's talk about decision tree. Decision tree is a very different kind of machine learning model from logistic regression and linear regression. Decision tree does not use gradient descent to learn because it does not really have like traditional parameters. Instead, it looks at all features in the dataset and splits the data into two nodes based on a feature threshold. And the most common types of trees called binary tree, that's the two nodes. Of course, you can have more complicated like three nodes, whatever, but even most machine learning models are not like that. Then for these two nodes, each is split into more nodes, two smaller nodes, and the process continues. Okay, I will model a sample process for you in a little bit. Okay, the splitting process should give us the most information. So that is how, that is like for linear regression, we're trying to learn which parameters are the best. And we try to minimize the loss function. But for here, there's not really loss function. Here, we're just trying to have the best split so that it gives us the most information. And what does that even mean? That means we want to try to make each split be more pure. So there's something called entropy. It measures the disorder of a node. And Gini score is also another similar. The formula is very similar to entropy. We don't need to go into the actual complex formula, but just understand that entropy is disorder of a node. And what do I mean by disorder? Well, let's say we have 10 samples, and 5 is class 0 and 5 is class 1. Then 0, 0, 0, 0, this 5 zeros split, and 1, 1, 1, 1, this split, this kind of split is the best possible, right? So this is very pure. So for this node is very pure, for this node is very pure. Because just one class. However, okay, and by the way, this is a typo. This is a typo. This is supposed to say 0000 and 011111. So here we are splitting a 4 by, so here the node has 4 things, here the node has 6, that's fine. It does not always have to be like a equal split, that's fine. But here, even if we have like more things here, because there's a 0 here, the entropy cannot be the smallest possible, because there is some disorder here. Okay. However, this kind of split, you can see it is much better than this kind of split. You can see here, there's both zeros and ones and both zeros and ones, and it's all mixed. So mixed means high entropy. That is not good. We want lower and lower and lower and lower entropy. The feature threshold with the most entropy decrease wins, and the process is further propagated now. And I'll show you what that means. Okay, and then we'll talk about this figure. Okay, so let me go to here. Okay, so here's an example. Let's say we have this data set. So let's say we have a feature called color, we have a feature called height, and we have a feature called is this person happy? And the color is his favorite color. So let's say somebody is red, somebody's favorite color is blue, and then red, and then blue. And then the height is like 5.5 feet, 5.1 feet, 5.2 feet, and 5.4 feet. And this person is not happy, not happy, not happy, happy. So here is how we model what a decision tree would do. So right now we have everybody, and let's say this is 1, 2, 3, 4. This is the index of the people. So they're all here. Let's say the tree finds that the best like splitting threshold is height is greater than 5.3, and on this branch is height, of course, less than equal to 5.3. So then what do we have? Well, we can see that greater than 5.3 is 1 and 4, and then less or equal to 5.3 is 2 and 3, right? Well, 2 and 3, they're both already part of the 0 class. They're both not happy. So if you split more, it doesn't even matter, right? So this, we're done. But for this one, what's a good split? Well, they're already both more than 5.3, so what should we look at? We can look at color. So the color might be, we want the set. If it's just red, you go over here. If the color is blue, then you can go over here. And right now, I only use 2 colors. But if, let's say, there's red, blue, and green, then maybe on the left, it could be color is red or green, and on the right, it could be color is blue, something like that. So it's just subset of the categorical features. So notice that for numerical features, we define a threshold. For categorical features, we do subsets. Okay, well, the person whose favorite color is red is 1, person whose favorite color is 4. So this is good. So you can see here, right here, for this 1 and 4, 1 is not happy, but 4 is happy. So the entropy is not the lowest. But when I make it to be just 1 by itself and 4 by itself, then the entropy is decreased, and that is good. Okay, so some things to note, and you can write this down. I'm not gonna write this down because it's already in the notes here, but just listen to my summary, and you can write this down if you want. So first, all trees you'll see in machine learning are binary. Second, so the algorithm is basically, we look at each node, we find the best feature to split, we find the best feature and the threshold to split on. And then we see, is that split, will that split actually decrease the overall entropy? If it does, then make the split. If it doesn't, then we stop. And when we stop, these are all called nodes, right? But the final nodes right here, there are no more splitting. It's called a leaf. It's called a leaf, or you can say leaf node. So for each node, let me reiterate. So for each node, we'll find the best feature and threshold to split. But if that split does not even decrease the overall entropy, then we should stop, and that's it. So when the tree is fully constructed, you can see here's my training data set. But when there's a new test sample, what do? Well, I'll just see, oh, is the test sample's height more than 5.3? Okay, it is. Then let's go over here. Is the color blue? Okay, it is. Then let's go over here. Then I end up with this leaf. So how do I predict the label? Well, for classification, you just predict the majority in each leaf. So for this one, there's like 0 and 0 here, right? So for any test sample that lands in this leaf, the output is just 0. For any that lands in this leaf, the output is 1. And for any that ends in this leaf, the output is 0. Okay, for regression, what we do is we just take the mean of the samples. So for this training sample, we'll just take the mean of these. It is a number, and then we just output that number. So for regression, you can see that many test samples, although they're different, we will just predict the same exact value because we're just giving them the mean of the trained samples that went to this leaf. So that's a little bit not like linear regression. Linear regression, if the test samples are different, when you multiply by the theta, it'll definitely be different. The Y prediction will definitely be different. But for trees, it will not. Okay. So here's like a real life example of a tree. And you can also output these kind of graphs in StandardScaler. So this is the famous iris data set. So here is the feature. You can see the threshold. We're saying less than or equal to 2.45. If that's true, then go over here. If that's false, then go over here. You can see the Gini scores right here. So look, this is 0.6667. Here, the Gini is 0. Here, the Gini is 0.5. Oh, well, I can clearly see that when I split, the Gini decreased. The total Gini decreased. That's great. You can see here, the split is insanely good. For this split, I got 50, 0, 0. That means everybody is of the Setosa class. Then I'm done. There's no more splitting needed to do. But for here, I have two classes. I have versicolor and I have virginica. So what should I do? Okay, let me find the best parameter to feature to split on is petal width. And then I have these two nodes. And then I continue to split. You can see here. And for each split, I'll try to decrease the Gini score, right? Okay. So decision scores can be used for both classification and regression. Yeah. The main hyperparameters are max depth. It's the limit on, like you can see here, here is like layer 1, layer 2, layer 3. So we set a limit on how many layers it can have. And there's another important one, which is min samples leaf, is the minimum number of samples on a leaf to split further. So for both of these, if you want to prevent overfitting, you can decrease the max depth and you can increase the min samples leaf. And let's just think about why that is. So if I let the tree just split infinitely, it'll definitely stop at some time, but it might just make a split in the end that's just based on like pure noise. And it does not even like represent the data well. So if I say decrease the maximum depth, that prevents overfitting. And for minimum leaf samples per leaf, you can also think about that on your own. We're kind of running out of time. Okay. Another hyperparameter is the criterion. You can use Gini or entropy. Yeah. So here is the syntax. The library is called tree under StandardScaler, and you can import classifier or regressor. And again, you can set your own max depth, fit the model, predict, etc. And here, you can learn how to plot one of these plots if you want. All right. Now let's talk about random forest. So random forest is an ensemble of tree classifiers. So basically, random forest, so all of these, so let's say here is here's our X train. So what random forest does is called bootstrapping. Bootstrapping is we're going to sample randomly from this data set with replacement. And let's say there are like 100 samples. So for each sampling, and let's say we have 5 forests in this random forest. Then we'll sample 5 times randomly. And for each, we'll sample 100 samples, but it's with replacement. So definitely in each sampling, some samples are not seen, right? So we will train these 5 random forests on these sampled datasets. So these 5 random forests will not see the whole dataset at once. And then what we do later is we will let them all predict. Let's say we have a test sample, we'll let them all predict, and then we combine the prediction. Like if it is classification, then we can just do majority voting. If it is regression, we can just do the mean. So why is this good? Well, because when we do the random sampling, some trees will not get, for example, outliers, and some trees will. So by doing this, we can decrease the effect of outliers. Yeah. So it will lead to less overfitting because no tree can memorize the entire data set. And extreme errors from one tree get smoothed out by the correct predictions of other trees. So that's very important. Okay, the main hyperparameter is n estimators. It is just how many trees you want. And of course, there's the same parameters like max depth as decision tree. Decision tree is just one tree, but random forest, like I said, is however many you want. So here we're saying 100 trees and the max depth is 4. Yeah, and then the bottom is all the same. Remember that here's ensemble, not trees anymore. Yeah, and then for the interpretation, you can always learn a little bit more about like what I'm writing in the code here, but we're kind of running out of time to like explain each. Okay, now let's explain what is k-nearest neighbors. K-nearest neighbors is a very simple model, and it is non-parametric. I'll show you why it is non-parametric. So there's no parameters, but it is still supervised because we need an actual label to predict if we have a test set. All right, and it is mainly for classification, but also, of course, it can be used for regression. So it outputs a prediction by seeing what the classes for its k-nearest neighbors in the training set are. So that's it. There are no weights or biases, and all predictions are solely based on the training dataset. But of course, you need the training dataset. I need to know what my neighbors are, what the labels of my neighbors are, for me to predict a label for myself. Classification metrics is the same thing, the accuracy, F1 score, etc. The most important hyperparameter is n neighbors. So that is just how many nearest neighbors we want to look at. And also weights, but I don't think that is that important. Okay. The risk of overfitting is high when the n neighbors or the k is low. And I'll talk about why that is right now. So let's do a little example. So let's say here is some data. So the circles is one class and the triangles another class. So let's say we have a new data. The new data is right here. So what, and let's say the k is 3. So what are my 3 nearest neighbors? Well, it is this one, it is this one, and it is this one. Then what do I predict? Well, I didn't just predict triangle. It is class triangle because there are 2 triangles and there's one circle, then it's triangle. So that's it of k and n. And it makes a lot of sense, right? And if it is regression, then this point will have its own y value, and then all we do is just the mean of these y values. That's just regression. So now, keep in mind, this is a very important thing. It is that for classification, the k must be odd. Why is that? Because like this case, if I said k equals 4, if I made k equals 4, then the next neighbor is this triangle. Then I still predict triangle. But what if it was circle right here? Then I'll have a tie, and that is just, then I don't know what to do. So so in sklearn, if you actually pass the k as an even number, it will just give you an error. You cannot do that. But for regression, that's all fine. We're just taking the mean. Okay. And now let's talk about when k is low. When k is low, let's say I only look at the one nearest neighbor. K is 1. Then why is that overfitting? Why is that bad? Because then we'll just capture noise and outliers instead of the true pattern. Maybe my nearest neighbor is not representative really. But when I expand that to 3 nearest neighbors, then it's way more representative. But think about this. If I expand K to be huge, like 100 or 1,000, then I'll be looking at like every point in the data set. Then the majority class will just win. Like if there are more circles than triangles, then just circles will always win every time. So you cannot just have K be huge as well. So that's why it's an important hyperparameter to tune. So right here, it is the neighbors library under sklearn. And here, set your neighbors, fit, and predict, and that's it. Same evaluation scores. And for interpretation, again, it is non-parametric. In here, I did not introduce any parameters, right? But I did need to know the labels of X-string. So it is still supervised learning. There are no parameters like weights or centroids to output. Yeah. All right. Now let's quickly move on to support vector machine. Support vector machine is similar to logistic regression. There, we are still using a linear hyperplane, but so let's look at this diagram right here. So here we have two classes. What support vector machine does is it tries to maximize the minimum margin. And this phrase is just very important. You can write it down. You're trying to maximize the minimum margin. So you can see here's the minimum margin. Here's the minimum margin. Should I maximize this? Well, that makes a lot of sense. When you try to maximize it, you're just trying to find the best separating plane, right? But how's this different from logistic regression? Well, logistic regression, like we talked about in the first class, we calculate a loss for every point, and then we average them in the binary cross-entropy formula, right? You can go back to your notes to look at it. But for support vector machine, we only focus on these ones, and they're thus called the support vectors. So we only focus on them. We do not focus on other points. Okay. Of course, you can introduce nonlinearity again. You can use kernel and its kernel functions. If you're more advanced in linear algebra, you'll learn what kernel functions are, but it is basically just feature engineering. Like x1, I append x1 square, x1 times x2, x1 squared x2, log of x1, etc. Okay. Yeah, and I just said this, it maximizes the minimum margin. Yeah. Okay. Now, however, there's a problem, which is, in this case, you can see here, there's an outlier. So if I try to, there's no way to, so there, I cannot really do maximize the minimum margin because this guy is an outlier. What do I do? Like, I must have the separating plane here, but that also does not make sense. So in this case, which models real life examples where there are outliers, in this case, we need to have soft SVM, which is we allow some slackness. We allow some outliers like this. But of course, machine learning is all about trade-offs. So how much slackness? Well, that's determined by regularization parameter C. So you can tune that by yourself. But you need to know that C is proportional to 1 over lambda. And lambda is like the regularization up here for like Lasso and Ridge. So basically, higher C has a risk of overfitting. Higher C means lower lambda, and lower lambda means less regularization. So it has a risk of overfitting. So that you need to keep in mind. All right. Now, here is the sklearn syntax. It is SVM library. You can import SVC or SVR for support vector regression. And usually the parameters are good enough. The default ones are good enough. You don't need to set it. But if you want, you can ask AI or search documentation for what the parameters are. Fit, predict, that's it. Next, let's go to naive Bayes. So naive Bayes, in my opinion, is not even a very good model. That's not really like the accuracy or whatever is not very high, but we can still learn about it. So naive Bayes, it is based on Bayes' theorem. And I'm not gonna talk about a lot because that is you know understand more statistics for Bayes' theorem. But basically, why is it called naive? Well, it just assumes that features are independent. So that, like in real life, of course, that's not right. Features definitely are not independent at all. But it assumes that, and based on that assumption, it has different formulas of how to do machine learning. But yeah, so it is popular for text classification, etc. So basically, if what it does is if I have the probability of the word urgent in the, like, let's say, given an email is spam, what is the probability that this current email is spam given that it has the word urgent? So that might not make a lot of sense. So let me like write a little bit. So basically what it does is just we want to know the probability that y is a certain label, let's say the label is k, given all of the x. And Bayes' theorem is that is equal to p of all of the x given y equals k times probability that y equals k divided by probability of the x. So that's Bayes' theorem. If you don't understand it right now, that's fine. But actually, Bayes' theorem is very easy. Just like p y given x times p of x is p x given y times p of y. That's just Bayes' theorem. Okay, so for this one, this is what's the probability that we get a certain label given the x. So the predicted label should be like using notation from the first class, like argmax over k of this probability. So we just are trying to find the highest probability. Then that's our prediction. So naive Bayes has assumptions about this particular term. And this particular term, it just has the assumption like, oh, it's all independent. That we'll need to get into specifically. But yeah, so this is naive Bayes. Naive Bayes for classification, I mean, for regression, we use Gaussian. For classification, we use Bernoulli. And those Gaussian Bernoulli are just distributions, and that's further assumptions about the data. Like the data follows a Gaussian distribution, all of that. Okay, so here is the syntax. The library is called naive Bayes. We have all of these, and then we instantiate the model, we fit, and we predict, and that's it. But usually naive Bayes is not a very good model. Okay, so now we have two more models, and I'll briefly discuss them. They are all clustering methods. So the first is called KMeans, very famous clustering method, and it is unsupervised learning. Because to find clusters, we do not need to know the labels. But if you have the labels, then I can label this cluster, and then if a new point is close to this cluster, I can say, oh, that is that class. But to just find the clusters, it is unsupervised. So let me just use a new whiteboard to illustrate. So what K-means does is just this. So let's say there are some points here, and there's some points here. We'll initialize, you can clearly see there are two clusters, right? But we'll initialize two centroids. Let's say the first one we like initialize to here, and second one initialize to here. Okay, then what we do is this. We look at all of the points. All of the points that are near, that are closer to this one, get assigned to this centroid. All of the points that are close to this one get assigned to this centroid. And then based on that, we calculate the mean of the assigned points for each centroid, and then we move it to that new mean. So that new mean for this one might be here, so we move it to here. That new mean for this one might be here, we move it to here. And then we repeat this process. Because I moved, I now have a new set of points that are closer to me than closer to the other one. And if you want to do more clusters, then it's just closer to me than closer to the other centroids. And then I move maybe to here. And then this one, I'll move to here. And I do this iteratively. And based on common sense, you can also, there are proofs for this, but based on common sense, you can also see that, oh, I should be able to converge, right? I should be able to converge, like when I move to here, all of these points are closer to me. When I move to here, all of these points are closer to me. I'm done. I will move no more. And then we have these two centroids, and then we found it. we found the centroids. And then if a new test sample is like here, well, which centroid is it closer to? It's closer to this one, so I'm gonna say it's this cluster. However, this is just like gradient descent. The convergence, I do not guarantee that it will work. It depends on the initialization of the centroids, just like gradient descent, like we talked about last time. So we must have many different initializations because the algorithm is not guaranteed to find the global min. Okay. So initializations, we have many. So that is governed by this parameter, hyperparameter. So here we're just gonna like initialize with 15 centroids and we'll find which ones are the best. And for K-means, remember, you need to specify the number of clusters you want. So if like I specified here, 3, then that means I want to make 3 clusters out of my whole data. So that you need to specify yourself. Okay. And then here, remember, it's just scalar, not cluster, and fit, predict, etc. All right. Finally, you can also, like interpretation, you can also print out like the cluster centers, the actual centroids for you to like visualize. That's also pretty fun. Finally, let's talk about DBSCAN. So DBSCAN is density-based clustering. DBSCAN is famous for these types of cases. So the first case is like interlocking like rings. So like there might be 2 clusters like this. Well, of course, the top like half circle is a cluster, and the bottom half circle is. But if you do K-means, K-means is spherical. Keep that in mind. K-means is spherical. So if like maybe K-means will find this centroid, and then this is all of one thing, and then this is all of one other thing. But that is really bad, right? That is not the actual thing. Another famous case is concentric circles. Like this is one cluster and this is another cluster. Well, K-means usually, oh, like it'll find like this and then maybe another centroid here and then like those are the clusters now, but not the interlocking, not the concentric circles. So that is bad. So what DBSCAN is basically, it is just, so let's have the interlocking rings again. So this is one cluster and this is another cluster. So what it does is each point, we have a little radius. So, and you can see here in the notes, there is like a core point, border point, noise point, but you don't need to understand the like exact like definition. So basically it's just, we have this point, and then maybe this point is also in the radius, but that is also a border point, and this one is also a border point. And there is like these circles, this radius for me to consider. And then we basically like propagate along until we can add no more points. So you can see that this is like density based, right? If you're not inside the circle, then we're done. But if you're inside the circle, then you're part of my cluster. So DBSCAN will do this. It'll just say, I'm going to iterate through all of the points in the dataset. Let's say the first point is this one. Well, this one, let's start a new cluster and then like propagate. Use the density algorithm to propagate. And let's say this one got all of these points. And then the next step in the algorithm is to just, okay, I'll go to every other data point, but let's say, like, I'll go to this one. Oh, is this one part of a cluster? Yes. Okay, I'm not going to worry about it. Is this one part of a cluster? Yes. Is this one part of a cluster? Yes. When I go to this point, it is not part of a cluster. Start a new cluster and then propagate along. And then let's say we find another this one. And then we're done. So, very important. You can see that DBSCAN, I do not need to tell it how many clusters I want, right? I do not need to tell it. Like K-means, I told it I need to have 3. I can also tell it I need to have 4. So for K-means, let's say like there is cluster here, there's cluster here. There's 2 clusters clearly. But I can also say, give me 3 clusters. Oh, then it might like find this one. Sorry. Then it might find like here's a centroid. Here is centroid, and here's a centroid, like 3 centroids. It might find that. But for DBSCAN, it will not do that. DBSCAN is it is non-parametric. So you not need to specify how many clusters you need. All right. So here, again, it's sklearn.cluster, and then you instantiate the model, and then you can give it like these parameters. So eps is basically like the radius of the circle. If you want to, if it's bigger, then it will have a wider like radius. It will look at more density like that. For minimum samples, it is number of samples in neighborhood to be considered a core point. Okay, so that is it. All right, so we can now take a break. We can now take a 3-minute break. But let me say two more things before we take a break. So first, uh, because we're kind of running out of time, I did not explain a lot of like these interpretation points, but definitely for the competition, it is important to always output graphs or output tables and output all of those so that you show that your results are meaningful and correct. Yeah. And the second thing is I sent in the Zoom chat the link for the registration for the final showcase. Let me just send it again. So you can use this time to register if you want. Yeah. All right. Let's take a break. We'll come back after 3 minutes. You can ask any questions in the chat or unmute. Okay, everybody, please come back and we will start the second part of our class. So for this part, we will solve a real problem step by step. So I'll actually code out stuff. So the thing I selected is e-commerce shipping data on Kaggle. And one thing to note that is on Kaggle, many people like they have already done a lot of code, they have already done a lot of analysis. So please do not use that. If you what you write yourself, and we'll also test your understanding. So you need to be able to understand what you write. You can use AI to help you, but you need to understand what you write. And yeah. Okay, let's get started. So this is e-commerce shipping data. You can download it right here. You can directly download the CSV. Let me sign in with Google. Okay. It's called train1.csv. So for Google Colab, we're going to be doing our presentation and you're going to be doing your coding in Google Colab. So right now you have your data. We need to connect to a runtime, and it's automatically connecting right now when I open the files. So, okay. And I upload my train1.csv. You can rename it, but I'm just not going to rename it. Okay, let's get started. So first of all, if you want to code, you have to know the important libraries. So here are the important libraries. So we have NumPy as NP and pandas as PD. These are for data. These are for data manipulation. And then you also have matplotlib.pyplot as PLT. That is for making graphs. Okay. Now, let's read our data. So data, we read it as pd.readcsv, and then we have our data, so it's train1.csv. And then we can print the head. So data.head basically means print the first 5 rows. Okay. If you want to do 15 rows, right here. So you can see here is our data. We have the ID, warehouse block, mode of shipment, all of these. So the first thing you can notice is categorical versus numerical data, right? So warehouse block, it is categorical. Mode of shipment, it's also categorical. But for customer calls, customer rating, these are numerical. Product importance is categorical. Gender is categorical. And reached on time, that is the target. That's what we want to predict. We want to predict, based on all of these, if the product reached on time or not. Okay. So for the categorical data, right? For like mode of shipment, all of it is flight. But is every package delivered going to be by flight? No. So let's see what all the modes are. So let me print out the, first of all, warehouse block. So warehouse block, we have A, B, and D, F, it seems like right here. So let's print out the categories. And while I'm doing this, you can open your own Google Colab and follow along if you want to. So we have our data and warehouse block. We need to put unique on the here so that we look at the unique values. You can see that the 5 warehouses are D, F, A, B, and C. Now, we can do this for each of the categorical variables. So first of all, we have mode of shipment. We also have product importance. We also have gender, but of course we know that gender, it is just male and female. So right here you can see all of the categories. So flight, it can be flight, ship, and road. Product importance is low, medium, high. Gender is female and male. Okay. Now, we need to follow this checklist, right? we need to follow first exploratory analysis. So what do we do first in exploratory analysis? We first check the missing data, right? So let's see if there is missing data in here. So what we do is we print the data and then is not. This makes the data into a Boolean mask, and it is true if it is missing data. If it's false if it's not. And then we sum it along the rows to see for each feature. There's no missing data, so we do not need to do anything. But in the real world, the data sets that you'll get, some of them will have missing data. So what do? Of course, you can delete the rows if the amount of missing data is small, or you can use imputing, and you can let AI help you with that. So we have no missing values. Now what do we do? Let's see if there is class imbalance, because class imbalance, as we have said in the first class, is a it's a very severe problem. Because if only 1% of packages are delivered, like are not delivered, well, if the model just predicts it is delivered, then the accuracy will be 99%. And that's such a good accuracy, but it did not even learn anything. So we need to solve class imbalance. So I'm going to print the number of, yes, it is delivered on time. How I do that is data, and we're going to do reached on time, dot sum. Because for reached on time, as you can see here, it is 1 or 0, right? And 1 means it is reached on time, 0 means no. So if I sum all of all, the ones, they all plus 1, but the zeros, they don't do anything. So the sum, it will look at how many packages were reached on time. And total can do the length of the data reached on time. Let's run this. Oh, we have a little minor problem with parentheses. Oh, okay. Okay. So we see that the number of yes is 6,000. In total, there's about 11,000. So we can see that it is not imbalanced at all. It is not overwhelmingly yes or no. So we do not have to worry about that. But in the real world, if you have imbalancing, what do you do? Well, let's see. If you have imbalancing of data, then you can use stratified sampling, as we have talked before, in the training validation test set to represent the imbalanced class. We also have training class weights, so you can have class weight equals balanced in the constructor of the ML models, so that those classes will be prioritized. And also during evaluation, we will prioritize reporting the F1 score because, as we've said in the first class, F1 score is better for imbalanced classes over accuracy. And usually, tree-based classifiers like random forest, they handle imbalanced data better because they're based on entropy gain. So is how much more pure can you get? So if you're already very pure, you need to get more pure. So you're pushing the model to predict correctly those imbalanced classes. Okay, let's move on. Now, let's look at the correlation matrix. Because we know that features, right? Not all of the features will be important. And if one feature is very correlated with another, then it's very redundant and does not add information. That may even hurt the model. So let's make a correlation matrix. So we import Seaborn, which is another library. It's based on Matplotlib for graphing. And then we say the correlation matrix, it equals data.core. It is another function. And then numeric only equals true. So we do not want we do not want to use the categorical features because D, F, A, and B, those are not numbers. So how can you say this is correlated with that? You cannot really do that. So we do numeric only equals true. And then we do S and S dot heat map. correlation matrix. We annotate it. We do a color map for viewing, and FMT, which is the decimals, equals 0.2f. Okay. And then we show it. So here we can see a correlation matrix. You can see that on the diagonal is all 1. Well, of course, customer care calls and customer care calls, of course, they're going to be super correlated because they're the same feature. So if it's very correlated or very negatively correlated, that's very bad. So let's see which is bad. The only really bad one is discount offered with ID. You can also see that right here. ID was discount offered. But so do we delete the feature ID or discount offered? Well, as you can see here, ID is from 1 and then 2, 2, 3, 4, 5, 6. That is not, that is just the ID of the data. If we include that in here, the model might learn to memorize this ID is associated with this reached on time. So that's just memorizing data. That's not actually learning. So we're going to get rid of ID anyway. So even if this was not negative 0.6, we would get rid of the ID. But okay, we have gotten rid of the ID. All of these these look pretty good. There's not anything that is very positively or very negatively correlated. So we can move on. Okay. So let us drop ID right now. So data, we will do data.drop columns equals ID. And then we can print the remaining columns. So as you can see, we have all of our columns, but we do not have ID because we do not want to learn. We do not want to memorize the data. Okay. So now we have done exploratory data analysis. Now it's time for data preprocessing and feature engineering. Let's get started. So for feature engineering, right? For categorical features, what do we do? Well, it is one-hot encoding, right? Because the model cannot say A, B, D, F. Like, the model cannot really learn that. The model has to learn with numbers. So for categorical, we first list them all. So they are warehouse block, mode of shipment, product importance, and gender. So data, let's do one-hot encoding now. It's by a function called pt.getDummies. Because each one-hot encoded feature is like a dummy feature. So the columns equals, of course, are categorical columns. Drop first equals true. Remember, we have said before, this avoids multicollinearity, which is good for training. And then we make sure that it is integer. Okay, and then now we can print the columns again. We see that warehouse. We have warehouse B, warehouse C, warehouse D, and warehouse F. So that means, is the warehouse block B? If yes, then this is 1. Is the warehouse block C? If yes, then this is 1. And these are for all of these. We do not have A because we have drop first equals true. We also have the mode of shipment, which is road, ship, and flight is dropped. We have product importance, which is low and medium, and high is dropped. And gender, male, we have the female is dropped. Okay. So we have done one-hot encoding now. Now let's do scaling, because for numerical, how we preprocess data is scaling, because we do not want one of them to dominate the loss. So we need to actually get scalar, as this is shown before in our suite of ML models. sklearn.preprocessing, we import StandardScaler, and then we instantiate it, And then we need to do it only on the numerical columns, right? We cannot scale the one-hot encoding because one-hot encoding, that 1 and 0, that's not actually like a 1 and 0. That means true or false. So that scaling does not apply there. So we only do it on the numerical columns. So what are numerical columns? Well, let us just copy all of here, and then let's paste it in. Because this reached on time, this is our target. We do not want to standardize our target, right? Our target is 0 or 1. And these are all the one-hot encoded features. So we're also not going to standardize those. So here are our numerical columns. Okay. Now, data of our numerical columns, we're going to scalar.fit transform. And then data of numerical columns. And then we can print data.head. We would print the first 5 rows. So as you can see here, customer care calls before, as you can recall, it is like 44232. Now we have it is right here. So we have standardized it, we have turned it into a z-score. Same thing with all of these. And we can see that our target reached on time, it is not changed, it is not touched. And all of these one-hot encoded features, these are also not touched. Okay. Now, we have done normalization. Now we can do train test split, right? So let's do train test split for model selection. We import the train test split. And we do want validation, right? Because validation is for selecting which model is the best. It's for tuning hyperparameters. But unfortunately, sklearn does not have a native train val test split function. So what we'll do is we'll have to just do it manually. So let's first define x. So x is all of data, but we do not want the target. So we drop reached on time y and y, it is just the target. So we do reached on time y n. Yeah. So we can do x train temporary, x test, y train temporary, y test. And then we do train test split of x and y. And the test size, we're going to do 0.15 because we want to do a 70, 15, 15 train val test split. So we first split out the test. And then we can do random state of 42. Random state just ensures that every time you run the code, it's not actually, like, it's not going to be different. But it's going to be random, but it's not going to be different. So that is the first split. And then we do x train, x val, y train, y val. We do another split with x train temp, y train temp. Okay. And then test size, it was going to be 0.176. This is just to make it so that we have a 70, 15, 15 split. So random state equals 42. So, okay. We have now split the data. Okay. And you can see, you can see here, feature engineering. Feature engineering, the main method we have talked about is polynomial preprocessing, right? Polynomial feature engineering. But for this one, we do not really need to do it. Because first of all, we cannot do polynomial feature engineering on the one-hot encoded features because whatever times 0 is going to be 0. So that's useless. But for polynomial feature engineering, we can only do it on here. So yeah, if we wanted to, we could do like customer care call squared, customer rating times customer care calls, like stuff like that. But for the sake of simplicity, we're not going to do that right now. But when you're doing, when you're coding your model, try to do that and see if it helps or not, and make sure to not have the degree too high, or you'll end up with way too many features. Okay. So we're done with 2 and 3. Now let's do number 4, which is dimensionality reduction. So what is dimensionality reduction mainly for? It is for visualizing the data. But we can also use it for distance-based models because there's something called the curse of dimensionality. What that means is basically when you get to high dimensions like 100, points are all basically uniform apart. Like they've all become the same distance apart. Well, that might not make a lot of sense, but like it is on average, points are the variation of distance between points have decreased. So that's not good for distance, right? Because if everything seems like the same distance away, well, the distance models, they're going to perform worse. So PCA is also used for that. But for our data set, we're going to use it for visualization. Okay. So let's get PCA. And this syntax is also listed above in our suite of ML models. So this is instantiate a class. And we want in components to be 2 because we can see a 2D graph, right? That is good for visualization. And then PCA features goes pc.fitTransform. We're going to only do the numerical columns because PCA is not good for categorical. PCA, it is categorical. It's all either 0 or 1. But that's not good for PCA because PCA assumes it is like regular numerical data. So X of numerical columns. And then we're going to make that into a data frame. Okay. And then we're going to plot it using matplotlib. And just as a reminder, you do not need to know how to code all of this by hand. You can use AI to help you. And then a scatter plot. So we have df PCA. This is our new data frame. Let's plot our first dimension with our second dimension. But we want to differentiate between the yes and the no's because if we all just graph it all, it will just look like the whole distribution of data, but that's not really useful. We want to see which is yes, which is no. So for this one, we're going to have the condition that y equals 0. So this is the no class. And then here is just a little bit about formatting for the graphs. Okay, and then we'll label this one no. And then we will do another scatter plot, but this one is yes. Okay. And then plt.legend, make legend, and then plt.show. So we will show the graph. As you can see, here is what our data looks like because our data, numerical columns, how many are there? There are 1, 2, 3, 4, 5, 6. So we reduced from 6 dimensions to 2 dimensions. So there, of course, is a lot of information lost, but here we can get a good general sense. So here, as you can see, we have a big yes cloud right here. Here is some mixed yes and no's, and here is more mixed yes and no's. So here is a big generalization of our data. So here it is relatively like unclean. It's relatively messy because when you're in here, you do not really know if you're yes or no. But in other data sets, probably the ones you choose, it will be more clean than this one. So you'll see quite a clear separation between yes and no. Okay. Now, let's go to our final part, which is 5, 6, and 7, which is trying ML models. Okay. Okay, yeah. So right here, we obviously have a classification task, right? It is yes and no. So what are the models that we have shown that are used for classification? Well, number one, of course, we have logistic regression, right? We also have SVM, the support vector machine. We also have random forest classifier. And we also have a KNN. So when you're doing the competition and in real life, when you're actually training a model, you're going to test all of these because all of these have their strengths and weaknesses, right? For example, random forest classifier, it is good for data and balancing, and it reduces the effect of outliers. And like KNN, it is distance-based, which might be good, but distance-based also might be bad due to the curse of dimensionality, as I mentioned before. So you can see that all of these, they have their pros and cons. So you should, of course, choose based on your intuition, but you should choose all of them. You should test all of them to be safe. So for right now, we're going to do a very fast demonstration. We're just going to use random forest classifier. Okay. So let's instantiate it. For sklearn.ensemble, we import random forest classifier. Okay. And then we'll instantiate two models because I want to show you the process of hyperparameter tuning. So we use random forest classifier. Let's have in estimators. Let's not have 100. Let's just have 200. Okay. Max depth, the depth of the tree. Let's say 5 and min samples split, let's say 10. Because as you've seen before, our thing has 10999 samples. So we do not want super detailed of a tree. We want only the max depth is 5. So we only wanted to split 5 times before it is gone. So we do not want it to split so much that it is memorizing noise and like having super little overfitting little nodes. We do not want that. Let's have another model, model 2. Model 2, we can instantiate it. So let's have in estimators be 200 as well. But model 2, let's be a little more lenient. Let's say we can have max depth as 10 and min samples split equals 5 because as you can see, there might be some like fine patterns that we want to learn. And if you have such a simple model, we cannot really learn that. So let's just see model 1 and 2. Which hyperparameter setting is the best? So for both models, we fit it on X train and Y train. Okay. So it's training right now, it is learning, and as it's done. So you can see that learning does not actually take a long time. Only the like the deep learning models, they take a long time. So it is very realistic to try all of these and run all of these and see the best one. But yeah, in reality and what you're supposed to be doing, you're supposed to do grid search or random search because I only tried 2 hyperparameter settings. But for grid search, you can say, oh, okay, max depth, I'm gonna say 3, 4, 5, 6, and then 10, like 15. So all of those, and then min sample split, I can do like 2, 5, 10, 20. So something like that. So those, you should try every one of those because as you just saw, training a model, it takes a very short amount of time. So you want to try all possible combinations of hyperparameters to see the best one. So you gotta do grid search or random search or Bayesian search as we have said before. But right now I'm just gonna have 2 different models. Okay. So now let me uh let me evaluate them. Let's see which one's better. So sklearn metrics, we import accuracy because we're doing classification and F1 score. So remember, we use our validation set for hyperparameter tuning. We use our training set for training, of course. So right here, we use our training set for learning, for fitting, for training. We use our validation set for hyperparameter tuning, and then we use our test set at the very end to see one final unbiased performance. So yval pred for model 1, we're going to say model 1 dot predict x val is a validation. And then yval pred 2 equals model 2.predict. Okay, and then x val. And then we say, okay, so the accuracy for model 1. We use the accuracy score y test, sorry, not y test, y val, because we're using validation for hyperparameter tuning. And then y val pred 1. Okay. 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 So that is the accuracy for model 1. We can also do the accuracy for model 2. Sorry. It's not sorry, not y test, y test. Y val pred 2. And then up here is y val pred 1. Okay. So this is the accuracy. We can also do F1 score. And remember the F1 score, it is the harmonic mean between precision and recall. It is better for class and balancing. So we do F1 score. It's not y test. It is y val pred 1. And then we do F1 for model 2. Okay, let's run it. As you can see, it's very close actually. So for model 1, accuracy of 67%. And you see, oh, that's kind of bad, right? Well, it is kind of bad because right here, you can see that, yes, there is a big cloud of yes, we can accurately predict that. But you see right here, it's all mixed. There's not really a clear pattern you can learn. And it does it does make sense, right? For like packages, it is not super deterministic on these features, right? Packages like they might just get lost. And that's not determined by the discount offered or the weighting grams. It might have a little bit of correlation, but of course it's not completely deterministic. We cannot get a super high accuracy because if I reach them on time, it might just be due to a hurricane, right? So you see that the accuracy, it is not a lot, but it does make sense. Accuracy model 2, it is a little less. F1 for model 1, it is just a tiny bit more than model 2. So we can accurately say that model 1, it is better than model 2. So that is some rudimentary hyperparameter tuning. We tune hyperparameters, we see that this hyperparameter setting is better than this one. But in reality, it's up to you. Please do grid search or random search. Test all the possible hyperparameter settings. See which one is the best. Okay. So model 1 performed better slightly. Now let's look at the final test prediction. So ypred equals model 1 dot predict x test, and then we can do final accuracy, which is the accuracy score of y test and ypred. And then final F1, which is the F1 score of y test and ypred. Okay. Let's run this. So we see that the final accuracy is 0.67%. Rounded will be 0.68, and then the final F1 is similar. So that is the full process of training a model from start to finish. As you can see, we have done all of the necessary things. We have explored our data. We got to know it. And there are many things you could have done more. For example, of course, doing more hyperparameters, right? You should use grid search, random search to actually look at the best hyperparameters because I'm sure a random forest classifier, just this setting, it couldn't possibly be the best, right? So you should test logistic regression, SVM, random forest, and KNN. You should all test all of those and test many hyperparameter settings in each to see which one is truly the best. Yeah, and we want to leave it up to you to like choose and to explain your choices because that is what's yeah, and to explore each different model, and that because that's what's fun about machine learning. We've done data exploration. As you can see, we have visualized our data using dimensionality reduction using PCA. We have done data preprocessing. This is standardized for the numerical ones and one-hot encoding for the categorical ones. And this specific task is classification. But of course, if you want to do a regression task, it is completely fine. So that is the full that is the full thing. One thing important I did not do is feature engineering. So like polynomial preprocessing, you could have done that, and you should do that. Because the number of because like this pattern, it might not be completely dependent on linear custom calls. It might be customer care call squared, but you don't know. So that's what you should do. You can for like logistic regression, you use regularization, all the techniques that we have talked about. You should try to use it, and if it makes sense to use, then of course use it, and you should see which one is good or not good. So this data is I just searched on Kaggle and I just found it, and I just did a whole process. It's not really that hard. So it is I believe it's a very fun experience. So that is the essence of machine learning is to from data to get information, because you can have data without information, but you cannot have information without data. So that's what we're trying to do. We're trying to extract valuable information. We're trying to train powerful models for the improvement of our world. So if you want to, so as Victor has so as Victor has said in the chat, the final showcase sorry. The final showcase is okay. The final showcase is August 11th. Please register and yeah. Okay. And question is, can you share this notebook file so we can try to run after class? Yes. Uh, so this is what I just wrote, and it is based on this one. So right here. Here I've also said more, like I've explained all of the stuff, and it is more in detail. So I'll share this one with you. Uh, okay, let's see. So I'll make it, anyone with the link can view it, copy the link, and right here. Okay, and also send an email with this. Okay, and another question is how to know when to use PCA. Well, PCA, we all know that it is dimensionality reduction. There are two main use cases. The first is for visualizing data, as what we have done right here, right? Because for all our numerical features, we have six. How can we visualize our six-dimensional data? Right? That's kind of hard, right? Because our screen is 2D. The most we can do is maybe like draw a 3D graph. So to visualize our data effectively, we will use PCA to go from six features to two features, and then we can see that, okay, right here, most of this is yes, so the model can learn that, but these are mixed. And you can draw conclusions like this is mixed because it's not completely deterministic on the features, right? This is mixed because there's a lot of real life noise, so the model cannot possibly have that high of an accuracy. So that is number one. Number two is, I have said before, PCA is also used for distance-based models. So, what are some distance-based models you have seen? Like KNN, right? KNN is the K nearest neighbors, and how do you determine if it's near? It's the distance, right? Also, KMeans. KMeans is clustering, and clustering it is this group, this group, this group. KMeans is also based on distance. Another one is SVM, right? It's trying to find a hyperplane. and it's trying to maximize this margin, and this margin is the distance between the hyperplane and the support vectors, right? So for those, they suffer from the curse of dimensionality because uh think about it. If you have 100 features, right, in the 100-dimensional space, right? Because like how do you calculate distance, right? If you have a one point like in the 2D Cartesian axis, then x1 x1 y1 x2 y2. Well, what is the distance? Distance is the square root of x1 minus x2 squared plus y1 minus y2 squared. So it is the square root of all the coordinates, the difference of the coordinates squared. So when you up that to an 100-dimensional thing, it is x1 minus x2 squared. And then the y dimension, you do y1 minus y2 squared, and then the z dimension, and then whatever, 100 different dimensions. Do that. So as you can see, there are way more points who have a distance of 1 from a point. Right? Like if you have a point in 3D, all of the points that have distance is 1 is a sphere, right? Like I have a point right here. Here is the distance of 1, here's the distance of 1, here's the distance of 1, and that forms a sphere. In 2D, it forms a circle, right? So in higher dimensions, it is like a 100-dimensional hypersphere. And there are way more points on that than on a circle, right? Like, yeah, like a circle, it has infinite points, right? That we all know. But like in general, if you have a big data set, all of the points, they appear to have a more uniform distance. And that is called the curse of dimensionality. So if every point is about the same distance, how does a KNN perform well? Like, I have a point right here. The three nearest neighbors, well, the three nearest neighbors, they're all kind of similar to the five other neighbors, the five other near neighbors, right? So KNN will not perform very well in higher dimensions. So we can use PCA. You can see if PCA increases performance with KNN. But of course, a limitation of PCA is, of course, you will lose data, right? You're trying to keep the most amount of data when you are decreasing dimensions, but you're also losing data. So there's a trade-off between if I lose the information and I reduce the curse of dimensionality. So that is what you can explore in your Google Colab. So if you're trying to do a KNN, you can explore whether doing a PCA beforehand or not doing PCA beforehand is better. So that is when to use PCA. That's the second case. The first is data visualization. Second is for training the model. Okay. And another question is PCA used to remove noise? It's not really used to remove noise. It is used to decrease the number of dimensions, decrease the number of features. And like, it's not used to remove noise because noise, how do you know if that is noise or this is noise? You cannot really know. But PCA, it is used to keep the most amount of information. So like if a data set is distributed, let's go to let's do a new sorry. Uh okay. So right here, PCA, we want to do from 2 dimensions to 1 dimension. So let's say the data is distributed like this, right? It's kind of like elongated, right? So if we project it to this hyperplane, right? Because we want to go from 2 dimensions to 1 dimension. Well, most of these points are going to be scrunched up into this little area. And so that is a very big loss of information, right? Because these points are very far apart. But if we project it onto this hyperplane, they all appear to be the same. So that's a big loss of information. That's measured by variance. But as opposed to if we project it onto this hyperplane, Well, the data is elongated in a slant, right? So a lot of the variance is going to be kept, right? Because this is going right here, this is going right here, this is going right here. So that keeps variance. PCA is not about removing noise. It's about keeping variance and keeping information. It's about reducing the inevitable information decrease. Because of course you can express more in 2 dimensions than 1 dimension. But how do we try to keep most of that information? We'd use PCA. Another question is, okay, that's not a question. Uh, do you have more questions? If you have many more questions, then please ask in the chat. And I just want to emphasize again, uh, the deadline for the competition is August 11th. So please make sure to register before that. The competition, you'll need to use Google Colab. And Google Colab, maybe if you're in 7th grade and you have not learned how to code, that's fine. Google Colab, you can use like Gemini to help you code. But the most important thing is you have to understand what you're coding. You have to understand your choices. Because it's also true that Gemini also can make mistakes. So if you do not understand what you're doing, well, how are you going like then why doesn't just AI just replace you? So yeah, that's the essence of our competition. You can use AI, you can use anything, but use a machine learning model, use that innovatively, and use all of the techniques that you have learned to model a real life data set, model it goodly, and then you will win. So that is the premise of our competition. For searching up data sets, you can use Kaggle, as I have done right here, just the e-commerce shipping data. You can also use UC Irvine. So right here, wow, so many data sets, right? Like the Irish data set. This is one's a little bit like too famous. Like you should not do anything about this. And this is not really even useful, right? Like why do you need to classify flowers? It's not really does not really give a lot of like real world use. But like for example, like bank marketing or breast cancer, like those are more important. So you can choose some of those. And please make sure to uh follow our follow this follow this uh checklist if you want to like include everything and have the best model. So other than that, please ask questions in chat if you have any, or you can unmute directly. But if not, then I'll just wait here for a couple of minutes and yeah, thank you. Oh yeah, and it okay, and we go to documents. Yeah, here is a little bit about competition rules. We have already sent this out, but yeah. Let me just talk a little bit about the rubric. So, of course, we're trying to solve a problem in the real world with machine learning, right? So, of course, the problem and question it has to be clear. Like we're trying to predict, like in my example, we're trying to predict if a package is going to be late. And that can be very impactful, right? For example, if you're like working for Amazon, want to see what we can improve to make sure that our orders are going to their destinations on time and our customers are happy. We also have data collection, preprocessing, and usage. So how well you use their data and if it is ethical, but of course it should be ethical, right? And is there data leakage? Because as we have talked before, like the test set should be unbiased. The model has never looked at it before. So based on how you are preprocessing your data, we can see if there's data leakage and if you're using data appropriately and responsibly. Also, model selection and usage. Of course, this is just like the main part of machine learning. We want to select which model to use and why we use those models and how we use them, right? Like the hyperparameter tuning, everything. And we give a lot of points on interpretable results and conclusions. Because yeah, you have trained a model. Maybe you just gave your thing to ChatGPT and then you says, okay, please like do all this for me. But if you do not understand and you do not know how to interpret results, well, what are you even doing? So we emphasize interpretable results and conclusions. Like what kind of graphs do do you use for regression and how do you explain them? What kind of graphs do you use for classification? And and next we have overall significance and technical depth. So how well do you understand and like how much effort are you putting in? That is, we emphasize that a lot. And of course, we need to have clear and confidence presentation and communication. But I'm sure that we all can work on that. So right here is the competition rules. Please register for the competition. It is the deadline is August 11th. And we can use AI tools, but do not let that prevent you from understanding and or explaining. You'll have 5 minutes to present and 2 minutes for judges to ask questions. So that is all. If you have any questions, please ask in chat. I'll send this out and send the link to registration again. And yeah, thank you. And I'll wait for 5 more minutes to answer any potential questions. If you want to leave, then go ahead. Okay, we're going to end the meeting. If you have any questions, please ask us via Slack or email, and make sure to watch out for another email about the registration for the competition. And please make sure to do that. The competition will be on next Saturday and Sunday, August 15 and 16. And the deadline for the registration is Tuesday, August 11th. Thank you. Thank you very much for attending our 3-day workshop. Thank you. Thank you.